Yes, so let's go over to the second talk. So I'm very happy to introduce Stefan Lendl from Graz University. So he is currently a postdoc, and he also did his PhD at Graz University. And additionally, he's a COO and co-founder of S2 Data and Algorithms. So the startup develops Master Scheduler, which is a software solution applying robust optimization to holistic supply chain optimization. So very interesting for the robust community. And his research is based on both the application and theory of robust optimization. And he also published papers already in math programming. So very interesting work. And please, Stefan.
Thanks a lot for the introduction and the opportunity to present here in the seminar. Today I will present some of the theoretical work, which is joint work with Mark Görig, who is here also today, and Lasse Wolf from Graz University of Technology. And a quick overview of what I want to present today. So first, a very short intro, at least in this community, in two-stage adjustable robust optimization. Then a very short intro into the polynomial hierarchy and why it's interesting for us, basically, in this community. And then some results we were able to obtain, mainly focusing on the two-stage case. In the end, a few words on the multi-stage case for these kinds of problems. So let's get started. I mean, we all here know what classic robust optimization. You have a set of possible decisions, which we model by X, then some uncertainty sets, and I will be looking at primitive uncertainty sets, which model the set of parameters, scenarios that influence the different parts of our problem. And in the general version, you can write it like that. Everyone here basically knows that, and we hedge against the worst case. So what kind of uncertainty models do I want to look at today? I want to look at discrete and continuous budgeted uncertainty sets. So basically you have your vector theta, and in the continuous case, it's a real number between 0 and 1. And in the discrete case, it can be either 0 or 1. And we want that the one norm is bounded by some parameter gamma, so the classic budgeted setting. And in the discrete case, this means at most gamma values can be 1. And in the continuous case, you can also have some values, I don't know, 1/2 or something like that. So these very classic uncertainty sets. And since, as we know, the classic model is very pessimistic, two-stage models were introduced that model kind of the real-world setting that some decisions are made, then uncertainty happens, and afterwards we can still adjust parts of the solution. And this is called two-stage or adjustable robust optimization. So here we are looking for a first-stage solution X. We are maximizing, we have some uncertain objective function parts and some uncertainties in the constraints in the general case. And then, well, the adversary basically chooses theta, and this influences our uncertain parts of the model. And a common approach that's used is one often says, well, we can reduce uncertainty in the objective and just look at uncertainty in the constraints. And this is equivalent, basically. And so we develop algorithms for general uncertainty in the constraints. This is sometimes done. And we wanted to look at this kind of setting for different, of course, more specific cases, and understand the complexity of such robust multi-stage, or let's say two-stage kind of problems. So the tools we want to use are not just NP hardness and polynomial time solvability, which maybe everyone here knows, but we want to look at the polynomial hierarchy. Okay, and how hard do these problems become with respect to the polynomial hierarchy? And I want to quickly introduce what this meant with that, and more importantly, motivate why we should care about it. So there's this paper by Gerhard Wöginger, The Trouble with the Second Quantifier, that kind of did a review about this polynomial hierarchy and why it's important to operations research. Because the same way as NP hardness models hardness of finding basically polynomial times algorithms, we expect that there is no polynomial time algorithm for a problem if a problem is NP hard. And in the same way, the next level of this hierarchy that was introduced already in the 70s by Stockmeier kind of encodes something different. We expect that unless basically NP is equal to this next level of the polynomial hierarchy, we expect that then there are no polynomial size MIP formulations. So this is basically the, I don't know, hands-on interpretation of something being hard for a higher level of the hierarchy, is saying, well, if we could find a nice, small, meaning polynomial size, MIP formulation for our problem, then the problem must be in the class NP, because mixed integer programming is in NP. Okay, and this is why we should care about higher levels of the hierarchy, because often we have problems, and this happens very often for robust optimization problems, and it's one type of the examples in this paper where this hierarchy is important. There we have the case that we kind of don't know if a nice small MIP formulation exists, and then we can search for it forever, as we searched for polynomial time algorithms forever, until we had the tool of NP hardness to say, okay, we have some at least strong evidence that we can stop our search for a polynomial time algorithm. The same is the case if we can show hardness for the higher levels of the polynomial hierarchy. Because then, very likely, under the standard assumptions of computational complexity theory, we can stop our search, because we will likely not be able to find such a nice formulation. And we need different algorithmic techniques that are very commonly used in the robust optimization community to solve these problems. We cannot just throw them directly as a small MIP into the MIP solver. So that's the importance for the OR community. Just very shortly, what is this higher levels of, what kind of problems are in these higher levels? So NP is basically the class of problems where you're looking for some solution X that you can efficiently verify, right? So you find some solution is not formally completely right, but basically you find some kind of certificate, and then you can verify if this certificate for the yes instance is true. And for, think about the satisfiability problem. You are looking for there basically the true or false values of the variables are also your certificate, and if you know them, you can efficiently check if some formula is satisfiable. But finding it, we expect to be hard, right? So that's the first level. In the second level, we get more quantifiers. Like these are problems of the type, does there exist an X such that for all Y variables, there is a solution, that the predicate is true. So you have an additional quantifier. So if you think about satisfiability, you split your variables into two groups, X and Y. And the question is, does there exist an assignment to the X variables such that for all possible assignments for the Y variables, the formula is satisfiable? And somehow intuitively, you might think this is harder than just solving satisfiability. But, and the polynomial hierarchy is a way to really differentiate between the hardness of these types of problems. And the closeness to robust optimization somehow becomes clear from that, because we have this min max, or in multi-stage things, min max min problems. And they are somehow, you can write them in terms of multiple quantifiers. So this polynomial hierarchy is very interesting to robust optimization. And you, of course, can generalize and add even more quantifiers, and these then give the higher levels of the hierarchy. So that's just a very quick intro into this hierarchy of complexity classes and why it's interesting to operations research and especially robust optimization. And hard problems are known also for these classes. So there's also the notion of hardness. And for instance, this example of exists for all SAT, we can show that this is hard for the second level. So we expect it to be strictly harder than just satisfiability. Okay, so this was basically the intro. What results did we achieve by looking at our multi-stage robust optimization problems with respect to these tools? And if you look at general mixed integer programming, so you allow general MIPS, we obtained the following results. If you have continuous budgeted uncertainty on the right-hand side, so in the in the constraints for the right-hand side vector, we were able to show sigma free p hardness. So since we have a min max min problem or max min max problem, we are clearly in the third level and we were able to show hardness in this case. But if you have the same type of uncertainty and the uncertainty is just in the objective, the problem remains in NP. So it becomes, with respect to this hierarchy, strictly easier. So we can find a polynomial size MIP. So it makes actually a real difference where the uncertainty is and how much uncertainty we have with respect to the complexity. If you jump to discrete budget uncertainty, this changes again. So also the specific type is relevant, and we can become sigma free p hard, even if we have only uncertainty in the objective. Okay, so this is, to me, very interesting that we have this change, and so we can also expect different techniques to work depending on where we have the uncertainty. Then we also looked at very specific problems just in the with uncertainty in the objective, namely independent sets, the TSP problem and the vertex cover problem. And there, again, depending on the uncertainty, of course, this NP in NP result translates. And we get also for this very specific problems, the hardness if you have discrete budget and uncertainty in the objective. So are there any questions at this point with regards to the methods or the setting?
I do, if I may.
Yes, of course.
So when you talk about objective uncertainty, you mean first stage variable or second stage variable?
Sorry, I didn't.
When you talk about objective uncertainty, you mean the objective coefficient of the first stage variable or second stage variable?
I mean it exactly as we have it here. So we have uncertainty of the first stage variables.
In the previous slide, in the second stage.
Exactly, but it holds with the uncertainty. Let me show it here with the uncertainty as it's here. So okay, we have it only in the second stage. The first stage is not uncertain. And the second stage is uncertain.
Okay, thank you.
So we don't need the uncertainty in the first stage for the hardness result. Okay, so let's first come to the case of continuous budgeted uncertainty in the objective. And in this case, I said we are still in NP. So we have this kind of problem. We want to minimize the first stage decision, the adversary maximizes this scenario, and then we can do some basically adjustment or recourse decision. And if we assume that we have a compact convex set for Z, as we have for our two examples, f is a linear function in y and concave in theta. So even more general as the case I described before with linear functions, then we can apply basically Carat-Theodory's theorem and get rid of this alternating quantifiers. So get rid of min, max, min. So even if you would have more stages, you would end up with just minimization problem, max and then 1 min over some linear number of different y solutions. And under these assumptions, you can write down basically a MIP formulation for this. So this becomes a problem that lies in NP. So this was basically standard techniques with compact convex sets and just an application of Kara-Theodoros theorem. So in this case, things stay easy. But this, of course, only works in the case that we have continuous budgeted uncertainties. And in the discrete case, this application of Kara-Theodoros theorem doesn't work anymore. So for all other results, which are hardness results, we developed a technical tool and showed hardness for kind of a robust, adjustable version of satisfiability. And I think I want to explain quickly this problem because I think this can be used to show hardness of many more problems and could be useful in general. So let me quickly try to explain what kind of problem I mean here. So we say a SAT formula phi with 3 types of variables, x, y, and z. So we are looking at the standard satisfiability formula, and we split up the variables into 3 groups, x, y, and z. And we assume that it's given in conjunctive normal form. And in addition, we are given an integer, kind of a budget, gamma, greater or equal than 0. And the question now is there an assignment of the variables in x such that for all subsets of the y variables that are at most gamma, so the adversary can attack basically a subset of size gamma. If we set all the variables in gamma prime, so all the attacked variables to false or 0, does there exist an assignment of the remaining variables, so the variables that were not attacked and the variables in Z, such that our formula is satisfiable? So this is very similar to what we would call exists for all exists set, but there we wouldn't have an adversary, but the for all player could look at all possible assignments. And here we have some budget, and we can set the variables basically only to 0, not to 1. That's the difference. And this is closer to basically attacking kind of, or to this budgeted setting. And what we were able to show is that this variant of satisfiability is complete for the 3rd level of the polynomial hierarchy. So it's sigma 3p complete. And even in the case when all the variable sets have same size and all clauses in phi contain exactly 3 literals. So also the 3-set variant is complete. And this is a very useful tool that we use in all our hardness proofs. And the basic idea, I only want to show you kind of the idea why this is hard, is we use this standard SAT, 3-thread level SAT formula, and we create some basically special variables on the 2nd stage. Basically, we model setting something to true with an extra variable and setting something to false with an extra variable. And then we add some special S variables that basically can satisfy every clause. So for every clause, we keep the normal variables, but whenever there's a y, we add yit, and if there is a yi bar, so the negative literal, we would add this type of variable, and we add these S clauses. And then basically the adversary can attack the true and the false case, and this way we can model the hardness. I cannot give you the formal details, but this is the main idea. And you have the super gadgets. That's basically either you set as true or you get satisfiability as false, or you get satisfying all these clauses for free. So that's the main idea. The details, are a bit technical, as always with hardness proofs. Okay, so how can we use this now to show the hardness results we were after in the beginning? And well, one of the main results is that adjustable robust mixed integer programming with mixed binary recourse and continuous budgeted uncertainty in the right-hand side vector of the constraints is sigma-free hard. And sorry, I see here that, yeah, no, that's fine. The uncertainty is on, we need only the uncertainty on the right-hand side. So we do not need any other uncertainty. So we have no uncertainty here in the second stage cost, and we have no uncertainty in the B matrix. We only need the uncertainty in the right-hand side vector. And we show this via a reduction from this problem we just mentioned. And the basic idea that is needed is we just use the NP hardness reduction for MIP, because it's very easy, satisfiability. You can write also as a mixed integer program, basically. But the main challenge is, how do we encode the binary decisions of the adversary in our adjustable set with continuous budgeted uncertainty? Okay. And the main idea here is the following constraint, where also the uncertainty in the right-hand side comes in. We say, well, we bound such a variable set I prime. These are the respective variables in the MIP by 2 minus epsilon minus theta I. And this is a binary variable, so this bound by 2 would do nothing. And we go 2 minus epsilon minus theta I, and epsilon is small enough. And then what this does is it says, well, it doesn't help if you only use a tiny bit of budget here, because this would still do nothing. You would still be larger than 1 here on the right-hand side. What you have to do is, if you wanna basically attack set I prime, you have to use a significant amount of your budget. And this way, doing some technical estimates, you can show that basically you always attack fully, you attack in a discrete way. And this way we obtain the hardness also for the continuous setting. Which was kind of a surprising result for us, that we have this difference between, that we can really show it for a continuous setting here, the sigma-free hardness, if you allow uncertainty on the right-hand side vector. Okay, so let's now come to the setting where you also asked where do we need the uncertainty in the discrete setting. So we saw if you have uncertainty only in the objective function, then things stay in NP for the continuous setting. But if we go to this discrete budgeted uncertainty, things stay hard. And even for instance, the independent set problem. So sorry. So the problem we are studying is we want to find the maximum size independent set. Then some of the profits basically can be attacked by our adversary, and then we can do some recourse decision on what we search. And we are given an input graph. X is the set of binary indicator vectors of independent sets in G, and then after we do our second stage decision, it still has to be an independent set. So we select in the beginning some arbitrary vertices, and then some costs are attacked, basically, some profits are attacked. And then we wanna add some additional vertices, but those vertices must in total still form an independent set in our graph. So no two vertices that are chosen can be connected by an edge of the graph. And we are not changing the graph. So basically, this is the setting, and we were able to show that this is sigma-free P complete. And let me just very quickly try to give you some intuition on how this is done. We again take kind of a standard independent set reduction. So here we have the clauses. So it's a reduction from 3 sets, and you want to find an independent set. So for every variable here, you have an edge, and then you connect this literal, the other literal if x1 appears. So x1 appears, so we connect not x1. And then basically you want to find a larger independent set. So if you choose x1 here, then this clause can be satisfied because you can then take this vertex. If x1 would be false, you cannot take that vertex. And then this is the standard reduction, and we just basically blow it up and create this, use the similar reduction, but then say use our costs basically and the interdiction to model this, to model the recoverable adjustable SAT version by saying, okay, we have this first stage variables, and there we have only a profit if you choose them in the first stage. Then we have the second stage variables, and there we say basically they give you profit, but only if you choose the true variant, and those can be attacked basically. And then for the other variables, for the other gadgets, you always get the profit. So there's no reason for the attacker to attack it. And this way you see, we can use this nice SAT variant for which we showed hardness to quite directly use existing hardness reductions and show and apply and modify them to show sigma free hardness for the robust problem, for the two-stage robust problem. And this, for instance, works also for other problems. So you can take the standard hardness reduction for Hamiltonian cycle, basically for TSP, and do something very similar. So I think I'm nearly out of time, so I cannot explain any details, but again, it's a very similar idea. You take the standard gadgets from Hamiltonian cycle and use it to show the sigma-free peak completeness or hardness for TSP, for the robust two-stage TSP. So what's the outlook here? Well, on one hand, details of how to model uncertainty matter. We have seen this. And extra quantifiers matter a lot. And whether you use continuous or discrete budgeted uncertainty changes then the detailed complexity with respect to the polynomial hierarchy. And this also has implications on the kind of techniques we have to use to solve these kind of problems. So studying more details of the complexity landscape is really important to understand our kinds of problems. And as I have told you, well, kind of this technique we used to show the hardness kind of was very general. So we assume there is a meta theorem for discrete budgeted uncertainty. And we think that some generalizations of a result of Grüne might work also here. And I think he is already working with Lasse on some results, and some preliminary results are already there in this regard. So I think a meta theorem here can be proven to show a very general type of problems is sigma free hard. Then also some spoiler on the applications in transport optimization, just very quickly. So as Yannis said, we are on the applied front also working on applying these kinds of problems in transport optimization, since I know these kinds of actually the planning problem there is two-stage or multi-stage. So what we are here really working on and doing already is trying to bridge these models kind of really into practice. And I hope a colleague of mine is also doing her PhD now in this direction in a research project, and I hope in the future at some point she can maybe tell you more about that. So I really think we can apply really this two-stage nature of robust optimization here also in practice in logistics. So thank you, and I'm happy to answer any questions.